there is no way of getting something at frequency greater than 2 times the maximum frequency of the square, of the spectrum, when you raise it to the square. Make a convolution, you can get spectral lines, distributed part. All you want, suppose that this is 1 over 2t minus delta. The result will be 1 over t minus 2 times delta. You know? It's obvious. So to get something at 1 over t, the input spectrum must contain at least 1 over t. And that is the limit. That is the limit. Possibly it must contain something more than 1 over t. And then due to the cyclostationary nature of the input, what happens is that it becomes spectral line and blah blah blah. Okay? Let us see to this integral can be computed. This integral here can be computed in closed form. Let us write this like this: sigma a to the square and the other 2t. It is very easy. You put the raised cosine here, you find an expression that is as long as this of cosine, sine, alpha, 1 over t, 1 over 2t. A big number of terms, but you are very, very, very good in math. And so you can perform integration in closed form in less than 3 seconds by calling Wolfram alpha. Call Wolfram and say, please, Wolfram, tell me the result of this incredible integral. And he says, no problem. It is alpha divided by 4. Oh, what a nice result. My compliments to you. I will use your services again next time. I need to perform an integral. You put in place of g the raised cosine, of course. You must put there the raised cosine. And you do have the formula for the raised cosine. Use the formula only in the Roloff region, because we know that outside the Roloff region they do not overlap. So what you need to put into the Wolfram is only the expression of the raised cosine in this region. Okay? Only the shoulder of the spectrum. Put this here. Put the same here. Reverse plus the plus 1 sub t and blah blah blah. Integrate and get this. Beautiful. You see what with alpha, yeah, alpha is the Roloff. Roloff alpha. With alpha equal to 0, there is no amplitude of the wanted sinusoid. The timing recovery based on square law detection fails. With alpha that is non-zero, you get a spectral line with an amplitude equal to alpha divided by 4 multiplied by the sigma a to the square. Anyway, proportional to the Roloff. So you cannot exaggerate in reducing the Roloff. I know, reducing the Roloff is useful for reducing the bandwidth. But at a given point, also the amplitude of the timing wave is called the time, that sinusoid, this cosine is called the timing wave. The amplitude of the timing wave becomes so small that it cannot be used for clock recovery. And this can be a problem in practical implementation of time synchronization. So, we started by saying I need a sine, and what I get here is a cosine. No problem. It is a deterministic result. So I put a deterministic delay and I get the sine. This is the cosine. And so put here delay of t divided by 4. That is half pi in the phase of that sinusoid. And here you get the sigma a to the square by the amplitude in the case of the rising cosine alpha divided by 4, the sine of 2 pi t plus t0 divided by capital T. Then rectify and get the clock. Put it to the ADC and get the result. Here we have the Y. Questions? Do you want to recap the block diagram? The input is Y. I divide it into two branches. One goes to the ADC, the analog to digital converter sampler. In the technical language, it is called analog to digital converter. On the other branch, we have square law detection, low pass filter, delay, rectifier, clock. Questions? Is it clear? Suppose you are in a lab and someone asks you, please implement this scheme. Which is the first problem that you see? The first problem that you see. Which is it?
We need
continuous signal.
Yes, the signal is continuous. This is not a problem. This is the assumption of the problem. It is, you start from a continuous time signal and your boss says you, okay, my dear engineer with 100 cum laude, please sample it. It is a basic operation, passing from the continuous time to the discrete time for an electronic or telecommunication or something like that. Basic.
we need another delay because of the time of processing.
Yes. This takes time. It is not in the model, but anyway, this is in electronics. It will take time. This is a filter. It takes a lot of time before responding. This is a delay. And this is also in electronics. Ideally, these two are instantaneous. But in the practice, they don't are. But anyway, the filter for sure puts memory. For sure. So, here, what you find is zero memory. This cannot be done. So, if this block has a delay, which is not modeled in our mathematical model, you must put a delay here. So, please, my dear signal, wait for delta seconds while I'm processing you on the other path. Okay? It is like the buffer that we have seen in the last lesson about the feed-forward carrier recovery with application to optical systems. Please, my dear signal, wait a minute in that buffer while I'm processing you on the other path. And you see, this is exactly the same scheme.
Yes.
I'm processing you on this part, I need time. Please wait. So, one problem with this implementation is that this delay must be exactly known and must be recovered here. And we are not modeling this in our mathematical modeling. But in the implementation, there will be a delay that will depend on the implementation. You must check it, measure it, know it, and absorb it somewhere, for instance, here. And this is one of the reasons why this scheme in the fully analog domain is not so used. And we usually resort to another scheme, which is a feedback. Exactly as it happened in carrier recovery. In carrier recovery, we had two schemes. One in feedback, the other in feed-forward. It depends on the system and on the implementation, what you should use and what you prefer. Also, in this case, there is a feedback scheme for timing recovery, which is basically based on this. And here you have the feedback and the send. So, and since you would measure here the timing errors, as usual, the advantage of the feedback is that it brings the error to zero. And when the error is zero, it is a zero. And by the feedback, it is the system itself that forces the error to zero. Here you don't see what is the error. Why? Because this is, why? Because it is a typical error of Italians that try to express themselves in English. Why? Because it is open loop. You don't see the result. That is, you see the result after, in the further processing. But if the result is bad, nobody informs the timing extraction loop. It's done. It's finished. I've extracted the sampling, I use it. I get a bad sample. I don't know. I don't know here. I will see bad results here. But anyway, the timing recovery is bad. While with a scheme like this, the system works in a different way, because in the end here, you will detect the timing error, not the absolute timing, not the T0, but the difference between what you want and what you get. And automatically, the feedback loop brings this difference to small values. This is the property of feedback systems. Yes?
Don't we have a bandpass filter after the...
Yes.
Oh, yes, sorry. Bandpass filter. Band, yes, thank you. Pass filter centered over one over capital T. Thank you. Yes, because we must filter the sinusoid at 1 over T. Yes. So, the first problem that you can encounter with this system is that there is no control on the timing error. If you don't exactly know this delay, for instance, you don't know what to put here. And anyway, if the difference of delay is not under control, you will get better results, but nobody says to the timing extraction that the result is bad. While in this case, even if there are delays that are not under control in the loop, in the end, the loop will measure the timing error, the timing difference between what you want and what you get, and will drive this difference to zero in an automatic way. And so this kind of feedback loop is very, very often used in practical systems, especially where the loop can be closed quickly. And therefore, again, in radio systems, you will find this scheme. While in optical system, you will find this type of scheme. Or you can find this type of scheme. It depends. Anyway, with the timing, the problem of phase noise associated to the timing way is, let's say, less severe than with the current. So even in optical system, you can recover the clock in this way, even if there is a lot of delay in the loop. Because basically the bandwidth of the filter is so narrow that also the delay is not a problem. Even if you make an estimate of the timing error, with many sampling distance of delay, no problem, because there is virtually no random walk on the input, on the sinusoid contained here. The random walk is very, very small. Well, this is because while the carrier, take for instance a radio system. The carrier of a radio system can be at many gigahertz. For instance, 5 gigahertz or 50 gigahertz. The symbol timing is in the order of megahertz. And so the stability of the oscillator at megahertz is 1,000 times better than the stability of the oscillator at 1 gigahertz. Okay? So if you look to the spectral line, the width of the spectral line in frequency is proportional to the frequency. This is 1 giga. This is the width of the spectral line, which is a measure of the random walk. The greater is the step of the random walk, the broader is the spectral line. But if now you look to a spectral line at 1 mega, well, the width of the spectral line is proportional to the mega, while here it is proportional to the giga, and the optical system is proportional to the frequency of the laser. Okay? So, this is the carrier, because it is in the order of many gigahertz, while this is the waveform of the clock. It is in the order of megahertz for radio systems. 10 megahertz, 100 megahertz, that is the order. And so here the random walk is not a problem. And therefore, and the same with optical system. The carrier is at the optical frequency, frequency of the laser. The clock is at the frequency that is gigahertz, which is much smaller than the terahertz, I don't know, of the laser. So even in optical system, it is in many cases you can accept a delay in the loop. You know, we already talked about the effect of the delay in the loop. Okay, you remember? It is the shower. The shower with long pipes. So you are making the shower, you switch on the hot water. There are long pipes to the heater. Okay, so when you switch on the hot water, nothing happens. You go under the shower, it is really cold, very cold. Why? Because the hot water is coming, but it is not yet arrived because the loop is very long. There is a delay in the loop. Okay? And this produces instability because you go out, close, go in, it is always cold, then you stay under the cold water for a while and say it will become hot, it becomes too hot, you go out again, close the hot water, and so on. This is instability of the loop due to the delay. Okay? The only remedy to this is low bandwidth. Diminish the bandwidth of your filter. That is, don't open the shower, the hot water this way. Open the hot water a little bit with a small step and wait. You must have time, meaning narrow band, long time. You must wait. If you want to have a good shower with long pipes, you must wait and make small movements with the opening of the hot water. Move the, come si chiama rubinetto? Tap. Move the tap of the hot water a little bit. Put only your hand below the water and wait. After a while, it becomes a little warm. At that point, open a little bit and wait. Open a little bit and wait. That is, you can have the shower, good shower, also with warm pipe, but you must wait, be calm, and wait. Okay? That is, you must reduce the bandwidth of the system. If you can reduce the bandwidth of the system, then you can tolerate the delay in the loop. And this is exactly the lesson here. If there is delay, okay, you can tolerate it provided that you can implement a loop with narrowband. And you can implement a loop with narrowband if you want to track a sinusoid with narrowband. If the input sinusoid here has narrowband, okay. If it hasn't, you must do this. Is it clear?
去房租缴房租必须
The
得
last
本人缴吗？
thing that I should say is that here often you put a band pass filter over the frequency 1/2T. Why? Well, we have already said that what matters is only this part of the spectrum to the amplitude of the spectral line. So, why to put inside the square law detector all this part of the spectrum? It will give to you only noise, because it does not contribute to the amplitude of the wanted sinusoid. So it contributes to some other thing that you don't want. Okay? So, this is the input spectrum. The region that gives a good contribution to you is this one. The rest of the spectrum is useless to your purposes. It can only produce randomness. You don't want randomness. You want the sinusoid. So what you do is put a filter like this. At the output of the filter, you will have only the portion of the spectrum that contributes to the sinusoid, and when you make the square, you find only this part, which is really what contributes to the water signal. So this is called pre-filter. And this is called post-filter. And this, how is it called? What's the name of that part of the circuit? The square. How do you call this in technical language? Detector. Square law detector. Basically, we have two types of systems, filters and detectors. Non-linear systems, we call them detectors. And linear systems, we call them filters. So this is a detector. What is this to you? A filter or a detector? A delay of t divided by 4. In the technical language, you will have some... A filter, because a delay is memory.
Yes.
And all the linear systems are based on memory. So if you must choose between the filter and detector, for sure you choose filter. And how do you call this? Filter or detector?
Detector.
Detector, it is a nonlinear system.
Yes.
Instantaneous and nonlinear. So these are linear systems with memory filters. These are nonlinear, memoryless systems, detectors. Okay? Well, in my nose, yes, please.
Can we do a pre-filtering with a smaller bandwidth? The roll-off is not 1.
Smaller than the roll-off? Smaller compared to?
No. We use the 1/2t assuming that the roll-off is 1.
No, assuming that the roll-off is alpha. 1/2t plus alpha, and this will be 1/2t plus alpha. So the bandwidth of the filter is the roll-off region, whatever it is. If the roll-off region is 1, we use a wideband filter. As the roll-off region becomes smaller and smaller because we are reducing alpha, also the bandwidth of the pre-filter becomes smaller and smaller accordingly to alpha. So what I want to get after the pre-filter is only the portion of spectrum in the roll-off region, because only in the roll-off region I have a product that is non-zero in this integral. That is, only the roll-off region contributes to the amplitude of the wanted sinusoid. Everything is outside the roll-off region does not contribute to that amplitude, so I don't want it. And so the bandwidth of the filter is the roll-off region.
Okay, that is the center frequency of the bandpass.
Yes, this is the frequency 1/2t.
Okay.
I was saying that in my notes you will find also the details about the detection of the timing error. So here we detect the timing, the T0. Okay? Here we want to detect the timing difference between what we want and what we are getting. So the timing error. And there is a detector also for that. What happens is that here you must sample at frequency that is 2 times the simple frequency. But anyway, and here you go down. And here you will have the KT. The KT/2. But anyway, there is a detector also for this, for the timing error. Use the timing error detector and then filter in a feedback system. Okay? Look, find this on my notes.
Hey.